Today we're going to tackle separable equations. A separable equation is the easiest of the first order differential equation solving methods and represents when you are able to get all of the t stuff with the dt side and all of the y material with the dy side. So if you're able to separate your t's and your y's, or your x's and t's, whatever your two variables are, onto separate sides, then it is considered a separable equation, and from this point you would integrate. Sometimes you may not have a clearly separable equation, but you can make it separable, and you'll see an example of that later in this video. But to check whether a particular substitution would work, which is using y equals vx over here, or v equals y over x, you would check if f of xt yt equals f of xy. So let's go get to actually doing some of these example problems. I'm going to take a look at this first one in the handout, which is solve the equation dy dx equals x squared over 1 minus y squared. Now, this one is separable because I can put the 1 minus y squared with the dy by multiplying, and I can get the dx over by multiplying it to the right. So after I do that, I'm going to have 1 minus y squared dy equals x squared dx. And it's from this point, now that they are separable, that I'm going to integrate. And on the left-hand side, we have a polynomial, which is going to become y minus 1/3 y cubed equals, and on the right-hand side, that's going to be 1/3 x cubed plus c. I tend to put a c just on the x side, but if you had a c1 on the y and a c2 on the x, you can combine those into just a general constant term. So just adding 1 on one side, which is typically your dependent variable, or whichever letter is on the bottom of the dy, dx, dy, dt notation, that's going to be your dependent variable. And so over here, this is our solution. So let's look at another example, like this one. This is number 2. We've got dy dx equals y minus 3 times cosine x, all divided by 1 plus 2y squared. And so I see I could keep the cosine term on the right and multiply the dx over, and I could divide the y minus 3 over 1 plus 2y squared onto the left side. Now what that's going to give me is a 1 plus 2y squared over y minus 3 dy equals cosine x dx. And I want to now integrate both sides because it is officially separated. The left-hand side, I am going to need to be careful and think about how I want to manipulate that one. It's not very apparent to me what to do, but I see I have a higher power polynomial on the top than the bottom. So I'm going to do long division. So I'm going to take y minus 3 divide into 2y squared plus 1. And from here, I could see 2y times the y minus 3 is going to give me the 2y squared. So I've got 2y squared minus 6y. And when I subtract that line from the first, my 2y squares disappear, and I've got 6y plus 1. Now, dividing again, I've got 6, which is going to give me 6y minus 18. And if I subtract this line from the one above, I'm going to be left with 19. And that's my remainder. And so what this tells me is that my left integral is going to be equal to 2y plus 6 plus 19 divided by y minus 3 dy. And the right-hand side, integrating cosine x dx, that's going to give me sine of x plus c. So now I have to integrate this left side. So the integral of 2y is going to be y squared. Integral of 6 is 6y. And the integral of 19 over y minus 3 is going to be 19 times the natural log of the absolute value of y minus 3. And that's our final solution. Let's look at a third example. And here we have dy dx equals y minus 4x over x minus y. In this case, you're not able to separate the x's and y's on one side. If you multiply x minus y to the left, you're going to have an x dy minus y dy. So the x is stuck with the dy. Likewise, if you multiply the dx onto the right side, you're going to have a y dx and an 4x dx. And so that part's fine, but the y dx isn't, so you can't separate that. And so I'm going to check to see if substitution would work. So this is not separable, but I'm going to wonder, substitution? And so to do that, I want to check, is f of xt yt equal to f of xy? Now in differential equations, f of xy is your dy dx. So this ratio of y minus 4x over x minus y, that is f of xy. So when I substitute in f xt yt, I'm going to get the following: f xt yt equals yt for y minus 4xt for x divided by xt for x minus yt for y. And I notice that t can factor out, and so I'm going to have a y minus 4x over x minus y. And just to make it really clear, I factored out a t on top and a t on bottom. And so that I see cancels out. And what I'm left with is f of xy. And so that means that substitution will work in making it separable. So let's go ahead and apply the substitution. Now the substitution says that y equals vx. And so that's going to help us sub in for y, but we also have dy dx. Now v may very well be a variable dependent on x, and so y prime is going to be v prime x plus v x prime, but dx is 1. And when we make the substitution now into our original differential equation, what we have is that dy dx becomes v prime x plus v. And on the right-hand side, y is now vx minus 4x in the numerator and x minus vx in the denominator. I could see an x is going to factor on top and bottom, so I'm going to get v minus 4 over 1 minus v. So I factored out an x on top and an x on bottom, which conveniently canceled out in this case. And now I want to figure out, okay, this is supposed to be separable. So let me start manipulating here. First step, I'm going to get v prime alone. So I'm going to have v prime x equals v minus 4 over 1 minus v, and that is this v that I subtracted over to the right-hand side. I'm going to combine these terms and simplify. So this is going to be v minus 4 minus v 1 minus v all over 1 minus v. If I continue to simplify, I'm going to get a v minus 4 minus v, so those two v's are going to cancel out, minus v times a minus v, so that's going to be plus v. So that's going to be a plus v minus 4 on top. On bottom, I have 1 minus v. Ooh, sorry, that's going to be a v squared. There we go. So this is, let me write that out. This part here is v minus 4 minus v plus v squared. So the two v's cancel out. I've got a v squared minus 4 on top, a 1 minus v on bottom. And I've got this v prime, which is dv dx, x. And so now I am going to separate. And so that's going to give me 1 minus v over v squared minus 4 dv. And when I bring the x to the right side, I have a 1 over x. Remember, v prime was dv dx. So when I multiply dx to the right, I have dx over there. And so now it is, in fact, separable. And I want to integrate both of these sides. So on the left-hand side, I see that that is going to be partial fraction decomposition. Now I have gone ahead and done the partial fraction decomposition, but you should make sure that you can do it on your own. And what you should get is negative 1/4 over v minus 2 plus negative 3/4 over v plus 2 dv. On the right-hand side, when we integrate, we get the natural log of x plus c. So now let's integrate the left-hand side. We've got negative 1/4 times the natural log of v minus 2 minus, let's see, 3/4 times the natural log of v plus 2 equals the natural log of x plus c. Now remember, our original equation was dy dx, which means we want to solve for y as a function of x. The substitution that we made was y equals vx. So here we have v, which means v is going to be y over x. And so we have to make that substitution in. And that is going to give us negative 1/4 times the natural log of y over x minus 2 minus 3/4 times the natural log of y over x plus 2 equals the natural log of x plus c. And this equation solves the differential equation at hand. All that's left is for you to practice these practice problems at the end of the handout. Good luck.